Uh, yes, that's okay. Let me give the okay to the recording. Yes. To talk about how we want to test gravity with the stage 4 surveys, which are basically the current ongoing and about to launch large-scale structure surveys. That's what I'm mostly referring to here. And of course, I should mention among, as perhaps as the first one, Euclid, of which I am part, and some of you are also part, right? So Euclid is a ESA-led large-scale structure survey, but there's also the corresponding ones in the US, Vera Rubin, which started, and they just published some very exciting first light images a few days ago. And then we have the Nancy Grace Roman, which hopefully will launch soon. So Euclid combines photometric and spectroscopy probes. I'll say a bit more about that. And Vera Rubin is mostly photometry with the several bands in the optical, and the Roman telescope is spectroscopy. So basically combining all these surveys, we will have a very detailed atlas of the structure of the distribution of galaxies over an impressive volume, up to redshift 2 and 3, roughly. And this basically allows us to kind of open and finally open a new direction, right, into redshift, and finally study have a kind of volume with which we can study many properties of the universe. So far, most of what we have learned and the precision cosmology that we have been doing was thanks to the cosmic microwave background, so a kind of two-dimensional probe, just these photons reaching us from the scattering. And now we are going to kind of fill in the gaps, right, and map some 10 billion years of the history of the universe. Now, just a few more words. Maybe you are all familiar with the about Euclid. Some of these numbers should be slightly updated. But it's an almost all sky survey, right? So we plan to survey most of the visible sky in the north and the southern hemisphere, reaching some 13,000 or so square degrees, where we will measure the shape and photometry of with high precision for some billion galaxies, and then do spectroscopy for something like 30 million galaxies. The redshift range, what is interesting to notice also is the redshift range over which these two different probes will be working. When we talk about the photometric survey, we are going to basically go from redshift 0 to 2 and something. When we talk about spectroscopic, we are going to focus on the higher range. And that's mostly because of complementarity with other surveys, for instance, the ongoing DESI and the Roman telescope that will launch and so on, that will provide us with the spectroscopy at lower redshift. And just interrupt, I don't think I might see the raised hands, but otherwise just interrupt me if you have questions. Um, so just some more PR for Euclid. This is some beautiful cutout that was released some months ago. Actually, more than some months ago. Time flies. I think it was October 2024 when they released this patch of 100 square degrees from the southern hemisphere, but very close to the galactic plane. And it was just to basically show, this was 1 week of, 1 week, I think, if I'm not wrong, 1 week observations from Euclid, and just to show how sharp and what's the level of resolution that we are achieving with this instrument, right? How sharp the images are. And you can start from this cutout. There's a nice video that shows it. And you can keep zooming in, and and you can see more and more, and basically zooming into single galaxies, and you still see them at a very high resolution. So wanting to see the more than half full glass, Euclid is a beautiful instrument, and it's performing very well. Like every mission, of course, there's some issues here and there, but I think overall we are doing good. So let me, since I want to get to testing gravity and why do we even talk about testing gravity with such surveys, let me introduce and spend a few words about the two main probes, cosmological probes, because of course there's also a lot of legacy science that you can do with surveys such as Euclid, LSST, and so on. I'm going to focus on the cosmology. And that is gonna happen through these two main cosmological probes. I kind of hinted at them already when I talk about photometry and spectroscopy. So with the spectroscopic measurements, we build a galaxy survey, and for which we know with good accuracy the redshift besides the position of galaxies. And out of that, there's two main things so think about DESI and what DESI is doing in the lower redshift, and but this is what Euclid will do on a eventually larger area, sky area, and into deeper redshifts. So you have this atlas, very precise atlas of some 30 million or so galaxies. And out of that, we can study the full shape power spectrum. We can study the baryon acoustic oscillation, so pick up these wiggles that are similar to the baryon, coming from the same physics of baryon acoustic oscillations in the cosmic microwave background. And we can also probe redshift space distortion. So the distortion imprinted into the two-point correlation function because of the fact that we are measuring things into redshift space and then converting that into distances, right? And there's and besides the expansion of the homogeneous background expansion, the Hubble flow, there's also peculiar velocities, for instance, that impact actually the position of the galaxy, so can kind of change the relation between the distance and the redshift. Now, the baryon acoustic oscillation are instead a sort of ruler, wonderful ruler that we have in the sky, because it's kind of a circle that is imprinted in the galaxy, in the distribution of galaxies, as a region of slightly higher density of galaxies because of the remnant of these baryon acoustic oscillations, right? And then we can look at it at many different redshifts. And by doing that, we can kind of measure the Hubble rate. Basically, we have a geometric probe of the expansion rate, the angular diameter distance in one direction, and the Hubble rate in the other. So, but overall, it's a probe of background cosmology. From redshift space distortion, instead, we are probing into peculiar velocities of galaxies. So we are really probing into the growth rate of structure, because the relation between peculiar velocity and the overdensity brings into the game the growth rate. Well, this I think I'm gonna just quickly mention what is in this slide. It's a slide that was prepared, I think, by Marco Bonici. I like it a lot, and there's a lot of useful information on what physical questions you can address from galaxy redshift surveys. So what are the different things that you can measure? And I'm sure many of you are busy with Domenico on how to exploit baryon acoustic oscillation. So probably you know even more than me on this. The other probe is the weak gravitational lensing. So it's the distortion of light of distant sources by intervening ones that are in between us and the distant ones. And we are looking at the weak regime of lensing, right? Euclid, of course, is doing great also in terms of strong lenses. That was one of the highlights of the quick data release one that we had in March, where a significant number of strong lenses have been measured. There's been also the detection of a full Einstein ring. But for cosmological purposes, we are interested in the weak regime, gravitational lensing, which is a percent distortion. So we are after a percent distortion into the shape of galaxies. And the way we picked it up, of course, is by statistically, right? So we need big numbers of galaxies, and we need to look at the correlations of their shapes, and see whether there is any signal in there, which is basically then giving us a handle on the distribution of matter. So if you want, with respect to tracing galaxies, to looking at counting galaxies, those are like counting light bulbs, but it's visible matter that somehow traces the potential wells formed by dark matter, but there's a bias there, right, in how the galaxies really trace the halos of dark matter. If we do weak lensing, we have a more direct measurement of the underlying mass distribution. Of course, there's a lot of difficulties in here as well, and we need a wonderful point spread function, which is basically it measures the way your instrument reacts to a point source, and hence it tells you how well it will be able to resolve the shape of the galaxies. And that's one of the reasons, for instance, to go into space, to have a very small arc-second level point something, I never remember those numbers, 0.2 or so arc-second resolution for the images of galaxies. Okay, so why do we think that combining galaxy clustering and weak gravitational lensing can give us information about, of course, many things? Dark energy and dark matter is what we say, right? Euclid, LSST will shed light on that. But one of the things that they can allow us to do is to test gravity. So just to be clear from the beginning, when I say test gravity, I mostly focus on late times and the possibility that gravity on the very large scales of the universe is not really described by general relativity, but it could be something else. Now, I'll be very broad with the class of something else. It can be dark energy, so it can be in a dynamical alternative to the cosmological constant. It can be simply really, I don't even think about cosmic acceleration in principle. I would hope maybe to source it some in a way different than the cosmological constant, but I just look at the action for gravity, and I see whether that is really a good description. GR, the Einstein-Hilbert action, is a good fit to the universe on the very large scales. And why? Everybody can have different arguments for why. For me, it's just because we ought to do it. The way we convince ourselves that general relativity is a wonderful description of gravity in the solar system around compact objects is by using the parameterized post-Newtonian framework, right? So by building for ourselves a way of going around the GR solution. And so we thought about the different ways, different effects, physical effects that could be measured in the solar system, parameterize how they could differ from the GR, and then went on and measured these parameters, right? Very roughly speaking. So I think we have just to do the same now that we will have this data from the universe. It's a vastly different regime, much larger scales. There's the diffuse presence of matter and so on, right? Then, of course, some of the how gravity behaves on large scales could also be, and we hope it is, tied to questions such as what is the nature of dark energy, for instance, right? But I must say as a disclaimer that often the theories, when we look at specific models, they don't even try to offer a good alternative to the cosmological constant. Or often they solve maybe what is the new cosmological constant problem. They don't address really the old. So what happens to vacuum energy and so on. There's some cases that address these things. So I'm not gonna really push for one model. I'm gonna really more push for a framework that allow us to do a good surveying of how gravity looks and behaves on large scales. So, okay, this was a big detour. Now, just to make sure we have a common language, let me quickly review what we know about the background and large-scale structure in terms of lambda CDM, so standard GR to describe gravity, and a cosmological constant to source cosmic acceleration. In that case, we have a very simple Friedmann equation for the background and perturbations. If I want to focus, I'm going to ignore vector perturbations. And then I'll have the scalar part and the tensorial transverse transless tensors where gravitational waves live. So I'm going to use the Newtonian formula gauge for the scalar part. So I have these two metric perturbation phi and psi. Those are the relevant ones for large-scale structure. And if I'm late enough so that into the universe that neutrinos, the shear from neutrinos is negligible, then if you do the exercise of perturbing at linear level your Einstein equations and focusing on the scalar part, you find very simple equations. You find that phi and psi obey basically a non-dynamical equation, which in Fourier space becomes just an algebraic relation. They're equal to each other. So the first equation on the bottom left is just the Poisson equation, basically written in Fourier space. Rho delta is the density contrast of any matter source. And the one that obeys the dynamical equation is the density contrast of matter. And the interesting things to notice about this equation is that it's the same for any k. So, of course, it holds inside the horizon. So this describes what happens once the mode has entered the horizon. That's the only kind of mode scale dependence of this equation. Once the mode enters the horizon, it grows all at the same rate. So each mode grows at the same rate. And this rate is simply determined by what the background is doing. So if you know what H and A are doing, you know also the growth rate of your structure. And on the other side, you have gravitational waves, right? And so as long as you do your linear theory, you can kind of treat these two things as these two probes as separate. I'll comment on why I say kind of. Then, okay, so I'm gonna summarize in a nutshell what for me lambda CDM means when I look at large-scale structure surveys. It means something where acceleration is sourced by the cosmological constant, so the equation of state is -1. The two metric potentials are the same, and there is this simple scale-independent Poisson equation. Sorry, simple Poisson equation which gives scale-independent growth. Another way of saying in more qualitative terms what I just said is that the growth of structure is scale independent. That's a key feature of lambda CDM. Relativistic and non-relativistic probes respond to the same metric potential, and there is a consistency relation between the expansion history and the growth of structure. Now, let me see if I go, yeah, no, okay. Before I get to that slide, yeah, let me jump, I'll go back. I want to get to this slide first and the bottom of this slide. So by studying the dynamics of large-scale structure, so I'm talking linear, I don't think I will mention much of nonlinear regime in this seminar. So by, was there a question? No, just a noise. Okay. So by looking at how the question for your perturbations behave in a given theory, let's say you take F of R, a theory of modified gravity, popular theory of modified gravity, through the years we have been learning uh, that there are some common features, right? And Domenico was also very active in that field many years ago, right? That's when the famous mu and sigma then eventually came along. So there was, for instance, a paper by Domenico and Martin. I don't remember if Luca was also in that one or it was a different paper later.
Yes.
Yeah. So we have learned that in general, the growth of structure can be scale dependent, and it's not the big of a surprise because a simple way of understanding that is that what we typically do in modified gravity, we introduce, and I'll mention, I'll comment more about this, but we introduce a scalar field, and the scalar field comes with a mass scale or length scale associated to it. So basically introduces some scale dependence into the growth. The fact that we have some extra dynamical degree of freedom that can also cluster typically changes the relation between expansion, the simple relation between expansion history and growth structure. And the fact that there is indeed this, there are modifications that can, and an extra field that can have some clustering and some effective anisotropic stress, implies also that often the two potentials, phi and psi, are not the same anymore. Even if neutrinos are the shear from neutrinos is negligible. And so another way of looking at that is that if you follow the geodesics of relativistic particles, of those of non-relativistic, you are seeing two different potentials. So that's one of the reasons why we got excited about combining weak gravitational lensing, which probes the geodesics of relativistic particles, with galaxy clustering, which is basically a way of looking at non-relativistic sources. So just to be a bit more specific about what I mean with the modified gravity, this is going to just confuse you even more, but I wanted to show it. So this is nowadays you often hear about Hordesky gravity. And so I wanted to show the original Hordesky paper and action from 1974. So from some 30, yeah, I wish it was 30, some 50 years ago. Um, and so you see, it's a bit of a cumbersome way of looking at this action, but there's a very interesting story around all this, right? And I'm not going to tell it because then I'm going to run out of time. But let me just mention that Hordesky, at the time when he wrote this paper, he was a student of Lovelock. So Lovelock, the one of Lovelock gravity, of understanding what is the most general action that you can write in any dimensions in such a way that you propagate a massless tensor field. Then with Hordesky, he looked instead into what is the most general action that you can write in 4 dimensions, such that you propagate the usual massless tensor in graviton plus a scalar field with equation of motion at most second order, with the idea of avoiding very trivial instabilities such as the famous Ostroglassi ghost. So this is basically the most general action that Hordesky identify, and you can see that there's the metric as usual, and so therefore some geometric invariants entering in the action, but also the scalar field and derivatives of the scalar field. Now, there are some arbitrary functions. The modern way of looking at this action is the following, and it's what we call generalized Galileons. It's really the same thing. It was noticed eventually in around 2009 that what was becoming a very popular model for studying modified gravity, this container of generalized Galileons, they were nothing else than Hordesky gravity. So it's really funny because Hordesky started in 1974. Nobody really cared that much about this. Then cosmic acceleration came around and we started to panic and try to find ways of sourcing acceleration, explaining, kind of addressing the problem of the cosmological constant with dynamical dark energy, with modifications of gravity that were kind of, if you want, you can classify them using Lovelock theorem, right? I can break Lorentz invariance, I can give mass to the graviton, and so on, and so on, and so on. So many, many models were popping up. At the end, almost all of these are kind of subcases of Hordesky gravity. And it's obvious for some, like quintessence, k-essence, and so on. It's less obvious, if you want, for higher dimensional gravities, such as DGP, if you want. But that's by looking, if you take a kind of low energy effective point of view, and that's exactly by looking at the so-called decoupling limit of DGP. That's how Galileons were discovered and then generalized. So the message, the kind of qualitative message wants to be, no matter what you do to modify your theory, whether you give mass to the graviton, you introduce higher dimensions, you introduce explicitly scalar field, you introduce Lovelock invariants such as f of r and so on, function of Lovelock invariants in your action, you are gonna basically wake up a scalar degree of freedom. You have either introduced it by hand, or you are kind of waking up one of the degrees of freedom of the metric that was constrained in GR. So that's why Hordesky and generalized Galilean have become a very nice container. And this action is kind of a way of increasingly introducing more complicated terms. You start from something that could be just the potential. I managed to get sick with the hot weather. The potential and the kinetic term, simple kinetic term x, that I define on the right half page. But you can make it, if k is a non-trivial function of these, you can get into k-essence, for instance, right? Or you can start introducing what is a typical cubic Galilean term, which is this G3 box phi, and so on. More and more complicated, higher derivative, self-derivative interactions, and also coupling, non-minimal coupling to gravity. So G4, for instance, is the typical conformal coupling that characterizes theories as Brand-Sticky and F of R, but there's more. So that's kind of the, why do I have, okay. Yeah, I have Hordesky again because I just wanted to show that I met Hordesky. Last year is a really, really nice guy. And he's a painter, maybe you know, shortly after writing that paper, he became a painter. Then he kind of started to write papers again. They're a bit difficult to read, but he writes paper again now. After he discovered in around 2010 or so, through a student of Luca Mendola, he discovered that his theory was suddenly very popular. So that's a painting that he made with the theory, the Lagrangian of his theory inside. And we bought it in Leiden. So if you will ever visit Leiden, remember to check out the painting that we have in the department. Anyhow, so back to now, so I pause modify gravity for a moment, back to the props. So I mentioned BAO and redshift space distortion, and this is kind of a showing how we're gonna, with stage 4, we're gonna break into higher redshift and better precision, right? Better measurements of this. And so to kind of summarize, on one side with cleansing, we look at how light and relativistic particles follow their geodesics, and with clustering, what matter does. And basically, if we combine that, clustering and lensing, we have a way of testing whether the two potentials are the same. And also, if we combine BAO, so probes of the background, and probe of the growth of structures, such as redshift space distortion, we have another way of checking the consistency that is typical of lambda CDM. So in an ideal world, of course, right? There's many other things that we need to understand with these measurements, besides systematics and besides baryonics physics and many other things that we want to learn and understand. But in principle, we can also use them to test gravity. So let me flash how we want to test. So far I show the action for Galileans. I said most of the models we are interested in are in there. Now, we have done that exercise for a long time. I think for me it was during my PhD when I first started to play with the FOVAR and try to calculate large-scale structure in a FOVAR and so on, right? So it was the time when we were doing a FOVAR, people were doing DGP and so on. So really model by model, uh, calculating how perturbations behave and fit into the data. It can be successful, but it can be also kind of time consuming and not give you very satisfying answers. It seems also to be kind of a let me come up with a model and maybe I can feed the data. So I think it would be great if we find also another approach, which is let us kind of learn what the data want from the theory. And that's, I think, a way of looking at this broad phenomenological framework that is now I'm going to use the convention mu and sigma and W dark energy. There's many other letters there. And yeah, and there's many papers. And sorry, Domenico, for citing my and not being complete with all the citations. I just took the convention from there. So anyhow, the idea is the way we do it on the background, and so with the way we test for whether it is lambda or not, we introduce this equation of state, right? And then we check whether it's -1. And we can similarly do something like that for the perturbations. And we can check whether basically the relation between the metric potential phi and psi and the density contrast of matter is the one of lambda CDM or it's different. We can do that by introducing two functions that will be one in the case it's lambda CDM and can be different if it's not. To notice they can be not only function of time but also scale, because now we are looking at perturbations. So for instance, what they would capture in some models is the scale dependence introduced by the characteristic length scale of your model. If somebody, and I know some of you are, is very theory oriented, you can have many complaints about this function mu and sigma or questions, right? Can they really be anything? And how is it possible you have introduced a new degree of freedom? There's going to be extra dynamics. Where did this dynamic go? Because it meant that you had more derivatives in your equations. Can you still reduce them to just algebraic ones in Fourier space? How about locality and many other things? So these questions have some answers, and locality, there's something that you can look into and can impose some constraints on the form that these mu and sigma can take. What happened to the higher order nature of your theory, you should look at this as very phenomenological function. They just kind of tell you, no matter what your equations are, how more complicated they are, at the end of the day, if you solve them, even numerically, you will find that there is a modified relation between delta and psi and so on. So really mu and sigma is there to capture that, and also with the idea that at the end of the day, the observables will sort of give us not a direct, but kind of a hint about these relations. So indeed, this function has become a kind of the way of testing gravity. And so nowadays, any survey, any large-scale structure or cosmic microwave background experiment, besides telling you things about W, and typically through W0, WA, they will also show you something about mu and sigma. I think the first to have really a paper focus on modified gravity and showing things on mu and sigma from CMB was Planck. I think already some weak lensing survey were doing it before that. What are these contours telling us? That's a big question, right? And it's becoming an important question because these contours are shrinking. And we've seen it now with the buzz that the DESI results have created, because if you fit W0, WA to DESI, in particular in combination with supernovae data, you find a preference at some 2, 3 sigma level of deviations from the value the W would have in lambda CDM. Of course, there's a reasonable question to ask that I will ask, that is, how much does that depend on the parameterization? And that the questions apply potentially even more to mu and sigma. Because W is basically we have access to the integral of W over time. So it's, if you want, it's a bit less impactful, the choice that you make for parameterizing its time dependence. In the case of mu and sigma, in principle, by slicing up, doing our tomography of clustering and lensing, we can have a more direct way of probing them. And our results can be quite sensitive on the choice of the parameterization. So, yeah.
I have a question there. So is mu and sigma in the previous slide were dependent of K, and here I don't see the dependent of what happened there.
Right, right. So, yeah, thank you. I was forgetting to comment about that. Indeed, so the K dependence is often dropped for several reasons. The first one for practical reasons. I mean, it's much simpler to fit a function of time that then you parameterize with 1 or 2 parameters than to fit a function of scale, which would require possibly more parameters. So that's in most cases, that's the main reason. One justification could be that the K dependence is a direct reflection of the length scale, mass scale, if you want, of the degree of freedom that you have introduced. And most often, this scale is outside the range of scales that you are probing. That was kind of okay up to now, but I think it's gonna cease to be the case now that we are gonna go deep into the nonlinear. But it was the case that for models such as a Fauvar chameleon type, the scale is quite into the small, so outside of the linear regime. And for models more like cubic Galilean, Weinstein mechanism, the scale is very large. So, but yeah, but the true answer is we often neglect it just to make it simpler to fit. And I'll do it also in the exercise that I'll show. It's been done to also vary for K, but it's not done that often. Okay, so I'm typically very bothered by these questions of what am I learning here by these plots. I've measured W0, WA, mu0, mu-A. Have I learned something about the physics? And I think it will become indeed even more important as the contours shrinks, right? And this should happen with stage 4. So, well, I think I said already these questions, and another the first one basically, but another 2 things to mention that I will not touch upon in view of time is nonlinear regime. And how about the tensors? We are completely forgetting about that, right? We are kind of parameterizing only what the scalar regime, the scalar sector does. And we have learned from the hard way, from GW17 or A17, that you cannot just completely, I mean, if you want to modify your theory, you're modifying your action. Also, tensors will do something different, right? So I think some of these answers, especially the first and the third, can be addressed by combining this phenomenological parameterization, mu and sigma, with a more theoretical framework, which is that of effective field theory of dark energy. This was just a pictorial way of stressing the question that I just asked. So mentioning also how much, let me say this, since I won't be talking about the nonlinear, let me stress though that it's very important. There's a lot of information there, especially with stage 4 large-scale structure surveys, right? And depending on your probe, there's more information that you throw away. So but we are working on that. A lot of people are working on that. So there's going to be progress on the nonlinear. But let me focus on the linear part, and mostly the first question. Can I learn physics? And are these parametrizations? So I really like the approach of these phenomenological functions, but I'm not so happy at parameterizing them. Can I do something else? And can I use some more theoretical guidance for that? So what I'm gonna do is I'm gonna avoid making a choice for the parameterization of these functions, but I'm gonna bin them. And going back to your question, for now, I'm gonna focus on binning them only in time. You can do the same exercise, we've done it in the past, binning them in time and scale for mu and sigma. It's of course more complicated, and also the constraining power dilutes a bit, but it's definitely important to do it. So here, sorry for the color, so I'm not sure how much you see the yellow things, but here I'm looking at the big range in redshift from 0 to 1,000, and then I think I really want to focus on the late time universe and look at whether gravities G are there. So I'm gonna, and that's also where I have my measurements from stage 4 Raster structure. So I'm gonna slice very finely my redshift interval in that from 0 to 3. And then with addition of an extra node, a 4, and then some few nodes distributed with a hyperbolic tangent spacing, I'm gonna connect to redshift 1,000, which is basically CMB, where I assume for this exercise, you can do it differently, but for this exercise, I assume GR is recovered. So I assume all these functions go back to their GR value. And I'm not sure you can read, but besides mu and sigma, what I'm discretizing here is not W, but is omega of X. So I'm being a bit more generic. Instead of dE, dark energy, I use the word X because it could be something else in principle, some modification of gravity, but also some curvature that I could be picking up. And I prefer to work with density contrast rather than the equation of state. But the idea is I don't introduce a functional form. I bin them in time, and then I vary the values of this function in the bins together with all the cosmological parameters, and I fit to the data. So this the standard non-parametric approach. Now, yeah, I think I should probably speed up a bit. So data is just all data that we could. So this is a bit of an exercise, an old exercise from a couple of years ago. So you don't see DESI, you even see DS year 1. But it's all kind of data available at the time for background and for perturbations. So CMB, supernova, BAO, redshift space distortion, weak lensing, and so on. And so we fit all these to the data. And I'm going quickly here because I'll go back to these plots in a few minutes. But so here I'm flashing just what comes out of this fitting exercise. So then I interpolate, right, with a cubic spline. So I have some smooth functions reconstructed out of the data. And in blue and in red, you see the difference between whether I introduce also large-scale structures, so redshift space distortion and weak lensing, or whether I look only at background probes. And we could spend some time commenting about what we find. These are 2 sigma contours. So overall, we find good agreement with lambda CDM, which would correspond to the dashed black horizontal lines, with some hints from sigma deviating from the standard case. And that's kind of in pair with what mu is doing. And mu is having some departure in sync with omega to try to address some of the tensions of this data set. So that's also something that you have to be careful about, keep in mind, right? I mean, be aware that your data sets have tensions when interpreted within lambda CDM, and so whether you really want to interpret those as signatures of modified gravity or not, or of systematics. So, but what you could do, you could be a bit unhappy about this oscillatory behavior of this function. And also the question is, have we chosen, well, of course, we have tried different binning schemes, but have we settled on a good binning scheme? Are we overfitting the data? Are all the features that we see really physical or coming from some overfitting? So a good way of trying to answer those questions, there's different ways, but one that we like is by using theoretical priors. So I'm gonna just use, what do I have, some 5 minutes or so? This remaining time to say a bit about what I mean with theoretical priors. And so I mentioned already, right? We want to combine this phenomenological approach, which is let's put into mu, sigma, and w, or whatever data can tell us, and then I will worry afterwards. So the first thing you can do is a consistency check of lambda CDM. If it's not, then oh, it's not. Why it's not lambda CDM? Is it because of some new physics? Is it whatever? What am I picking up, etc.? And how to interpret, right? Any deviation from lambda CDM. So we do need some more theory guidance. And I think some help can come from folding in EFT or dark energy, which is this approach to, again, kind of parameterizing our ignorance about what gravity and dark energy could be, but using the language of symmetry and kind of writing an action, since we are interested in the linear regime, a quadratic action, which contains all operators that I can insert if I want to have my usual massless tensor and one scalar degree of freedom, but I have eaten the scalar degree of freedom inside the metric. That's why you don't see any delta phi or phi in this metric, but you see deltas of geometric quantities. G00, kappa is the extrinsic curvature of spatial hypersurfaces. That's a complicated language. It's the unitary gauge in which you basically adjust your spatial hypersurfaces to mimic, if you want, the perturbations that were really coming from your scalar field. Anyhow, it's just a language that allows you to kind of systematically write down all the operators, and some of these can come with a free function of time in front, besides some loose indices, time indices. And that's because you have you're using the argument of spontaneous breaking of time diffeomorphism invariance. Anyhow, this is really very equivalent to the actions that I showed before for generalized Galilean and Hordesky, but just in this case, I'm focusing on the perturbation. So think of this as the expansion of those actions at quadratic level in the perturbations, and just with another language. The nice thing of this is that now the freedom, instead of coming into those GI of phi x, comes through some few functions of time. So the way we use this action is to walk through the theory space. So we kind of create a Monte Carlo walk by varying at each step all of these functions that I hope you see them in yellow, this free function multiplying these operators. At each step, we make we draw a choice of this function. And since we have an action, we can check, a quadratic action, we can check if the choice that we make correspond to a stable model, a model that will not develop instability such as ghost, gradient. So basically will not lead to, if you want, very roughly speaking, to exponential growth of your perturbations, for instance. If the model passes, even though we have created kind of numerically, we kind of consider it one model in our theory space, and we calculate its cosmology. We predict its cosmology, and then we can calculate also what it is for mu and sigma. And doing so for many, many models, we create expectations. These are what I call theoretical priors. Theoretical distribution functions for the function mu, sigma, w. Again, we have created them in k and z, but I'm just showing a slice, basically a fixed k for mu and sigma. These are pure theory. It shows you out of sampling Hordesky what roughly you can expect. Now, if I want to use this information in the reconstruction, I'm not going to use the white line, the mean, because it can be quite sensitive to some of the choices that we make, modeling choices that we make in sampling these functions. But what we are interested in is the correlation, out and cross correlation, length, basically. So how the values of mu or in general of the functions are correlated in different redshift bins. That serves to kind of give us a minimum correlation length to fold into the non-parametric reconstruction. Sometimes this is folded in by hand. You can choose a kind of smoothing correlation length that you fold in. So just to kind of go to the result, out of this exercise of sampling the theory space, we create really a sort of theory correlation matrix. We fold it in with the data one when doing the reconstruction. And then you see now, if you look at the plots, the left column is what I had shown before, the reconstruction without any correlation prior. The right one is the reconstruction with this correlation prior. Hordesky, built on Hordesky, but really the model dependence shouldn't be so strong. It's smoothing away some of the correlations. So it should be telling us that some of those oscillations were really unphysical. We were overfitting the data. What remains, at least with this set of data, what used to remain was this tendency of sigma, capital sigma, the deviation in lensing, to be consistently above 1. So we looked into that, and really at the higher redshift range, it's related to CMB lensing anomaly. At the low redshift, it's instead more physical, if you want. It's picking up ISW and things like that. So I think that's a nice exercise. I'm going to skip on this, but you can also compare kind of how bad different parameterization do with respect to a non-parametric reconstruction. And I didn't mention I focus on mu and sigma. There's another function that you can use in alternative, right? You need only 2 functions to parameterize scalar perturbations in the linear regime. Alternatively, you can use gamma and define as the following, but really the physical meaning, it's the gravitational slip. It's the ratio between the 2 potential, phi and psi. And it's considered to be a kind of smoking gun of modified gravity. If you have gamma differing from 1 on large scales, that's typically because your theory is giving a speed of sound of tensor. There's a kind of connection different than 1. If you have it at small scales, it's because there is a fifth force at play. So with this data, the reconstruction, this is what it would give us for gamma. So I think it would be the most interesting function to look at. Because if it really crosses, similarly to what they've done in DESI for W, right? They cross the -1. If it crosses 1, it would be, if it's not 1, and even better, if it crosses 1, it would be very interesting in terms of giving us thoughts about theoretical implications. So I went a bit slow, so I wanted to comment a bit on the DESI results, but I'm gonna skip that. And perhaps I'm gonna just show one plot, 2 plots actually. So this, we did again a reconstruction of W in this time, not of omega, but of W with the DESI data. Because of course, like everybody, the first question we had was, is this deviation from -1 due to W0, WA? Is it just because I'm choosing that parameterization? And if you do, and also this itself, they did, if you do a non-parametric reconstruction, and here we skipped, for velocity, we skipped the priors. That's why you see several oscillatory features. But it seems not to be. There seems to be indication that indeed the crossing is preferred, even when you bin your functions. And so then the other questions that we asked ourselves is, okay, we want that behavior for the background with a crossing of -1, which is crossing of the so-called phantom divide, right? The regime of W smaller than -1 in quintessence is when you would develop ghost in minimally coupled quintessence. So which EFT operator allows me to go into that phantom crossing, into that phantom kind of regime. And in the left, we try, well, quintessence, standard quintessence, no surprise that you cannot go there. But we try also the different operators, higher order operators of EFT, those that had non-trivial self-derivative interactions. And they were not allowing you to go into the crossing of the phantom regime. I mean, it was really difficult. What made it possible quite easily was having a non-minimal coupling. That is no surprise. I mean, it's known, right? That a non-minimal coupling like the one in a Faubourg allows to cross the phantom divide. So I think these are interesting exercises, and we will be able to do more and more with the data that is coming. So I'm going to wrap up and just say that I think we are not anymore towards, but we are really into the era of precise and hopefully accurate cosmology, right? I think there's no question that we are going to get very precise measurements. The question is about accuracy at this point, both experimental, so if you think about systematics, but also from the theoretical point of view. There's many things in our modeling that can kind of lead us to inaccurate, if you want, conclusions, right? And one example that, again, I didn't spend time on is the nonlinear, also the modeling of the nonlinear physics. That's crucially important. That's something that can also kind of affect strongly the accuracy of your conclusions. But even the choices of parametrizations and many other things. What I show with the non-parametric approach, and that was already on all the data from a few years ago, is that, well, I didn't really give any quantitative argument and plots to support that, but the data has already a lot of constraining power. We can do better than that, just W0, WA. We can constrain, there is a way of counting the modes of gravity that you can constrain, and we can constrain several. And I think what it makes things even more exciting is that besides Vera Rubin with the LSST survey, the Roman telescope, and Euclid that is unfolding, and DESI that is giving wonderful results, we have also the frontier of gravitational waves coming up. Again, I didn't have time to go there, but there's strong synergy. If we modify the action for gravity, we might modify also how gravitational waves propagate, how they pick up relativistic corrections along the line of sight and so on. So there's a lot of interesting cosmology, I think, to do also there. And yeah, I stop here.
Thank you, Alessandra, for a very nice talk. Now we can have a few questions.
So thank you, Alexandra. This was a very beautiful talk. But regarding these tensors that you are mentioning now, are you referring to every tensor? I mean, a gravitational wave from astrophysical sources, or just the gravitational wave from primordial gravitational waves?
No, I was referring mostly. to the ones I had in mind, mostly the ones from resolved sources, mostly astrophysical. Those are the ones at least I've been looking more into. There's interesting stuff that you can do also with, for instance, CMB polarizations, and again, kind of measuring. Inferring things about your theory from basically measuring the primordial gravitational waves. So I think you can do both. I've been doing mostly the result sources astrophysical, so I've been playing a lot with uh, the fact that the conformal, what we call the conformal coupling, the non-minimal coupling, which is the one that was affecting that function gamma, right? So it's just whatever is multiplying Ricci scalar in the action. That has some very characteristic features in the large scale structure, but it has also some interesting features on the propagation of gravitational waves on the cosmological background. So also to be said, I'm focusing on the propagation. I'm not really focusing on the gravity in the stronger regime and waveforms and stuff like that. But I think even just by looking at gravitational, at the mergers as kind of single events, when we will have enough statistics, there's stuff, nice stuff that we can do. Yeah.
Thank you. I want to ask something on that because when you refer to the propagation, are you considering like the scenario where gravitational waves can propagate beyond, I mean, with a speed higher than the speed of light, like on your theoretical priors, is that scenario included?
Yeah, that's a very interesting question indeed. I hinted, right, the gamma that function, the ratio of the Newtonian potential. On large scales, uh, it's if you have a non, if you have CT squared, so the speed of sound not being one, that goes hand in hand with gamma also being different from one. And vice versa, if you constrain, so if you take GW17 or A17 to face value and you think it told us the CT square is equal to 1, full stop, then you assume CT square equal to 1, there is a way of kind of folding that in and projecting it into what you can then expect for mu and sigma. Because CT square equal 1, at least for these theories, this big container, Hordesky, means that on large scales, mu has to be equal to sigma. So there's interesting things there. When we look at all these things, we always treat separately the case we first constrain ourselves to CT square equal 1, but then we also open to CT square non 1. Where we haven't been able to treat CT square different than 1 is when doing gravitational waves themselves, the propagation on the cosmological background. We've been doing a lot of work on relativistic correction. So like you can do, like you do galaxy number count, you can do gravitational waves number count. And so you can build your observable, but that takes into account all the line of sight effects. And that we've been doing it for modified gravity, but it's way more complicated if CT square becomes different than 1. So that I have answers for that only in the case of luminal propagation.
Yeah, thank you.
Hi, so Alessandra, thanks for the
Okay.
good talk. Really, I have a question. When you do the construction of omegas, mu, and sigma,
Mhm.
or I mean, I don't know whether this is the case, but okay, you know that there is this sort of degeneracy between omega matter and mu because they enter in the, in the continuity equations. So when you do these theoretical priors, are you sort of breaking this degeneracy or no?
That's a very good question. I'm not sure I'm breaking it. I'm
Okay.
not sure I'm breaking it. Let's see. I don't think I have any expression that can help us there. So when I do the theoretical priors, it really means for each theory, I build up basically a statistics of what different choices of a theory will give for omega x and for mu. I don't think so. That's from the theory point of view. From the observational point of view, the way we treat the observables, also, I don't think we do anything to kind of break that degeneracy. And indeed, I must say that there is it's hard to see it. It took us a long time of inspecting these curves and these results, but there is a kind of hand in hand, if you want, a kind of degeneracy between what mu is fine in doing and sigma is doing. Sorry, omega is doing. So I don't think we have broken the degeneracy. It might be, it's a great question, because maybe one should think of using the observables in a different way to try to break it. We were really finding that especially S8 was playing a role here in a kind of forcing omega into doing something, which was then kind of reflected into mu, correcting for that at the level of large scale structure in another way. So yeah, I don't think we broke it.
So in a way, also in this plot, okay, with these theoretical priors, okay, probably you're fitting equations, I mean, data to you to the equations. There are, derivatives, first derivative, second derivative of the scale factor. So these theoretical priors actually, I would say, smooth all the behavior on doing the derivatives of the data, right?
Yeah, I think that's one way of looking at. That's one way of looking at that. Yeah. In reality, they sort of force. Yeah, I think that's one way of looking at it, because they basically force the correlation between different redshift beings. They kind of give you a correlation length, right? So, in very simple terms, they tell you on any redshift interval significantly smaller than the correlation length, there's no point of binning. I mean, you have a correlation length, there's no point on binning too finely within that correlation length, right? And if you do so, I will correct that for you, sort of. And probably the way it does correct that is basically the way you're saying, yes.
That's nice. Okay, thank you. Thank you so much.
Thank you.
Thank you, Alessandra. So let's thank again.
Thank you for having me. And yeah, I hope to come in person one day, Domenico.
Yes.
Let's